Something is building deep beneath the American Midwest right now, and it is going to change the geography of the entire United States, whether you are ready for it or not. What if I told you that the most destructive seismic event in modern history might be loading its springs right now? Not in 50 years, not next century, right now. The aging power grid stretching across the heartland, the transcontinental pipelines buried beneath the Mississippi, and the vulnerable brick foundations of the central United States are not separate liabilities, but the exact targets of the same unfolding catastrophe. Because here is what the geological models are showing that almost nobody is talking about yet. The new Madrid seismic zone, an invisible intraplate giant that previously rewrote the map of the continent on its own, is accumulating immense stress underneath the deepest, wettest sediment basin in the country. It is a tectonic time bomb sitting directly beneath the circulatory system of the American economy. No one alive has seen a mid-continent rupture of this magnitude, not once. We are going to answer the questions that the headlines aren't asking. Why is this subterranean fault so fundamentally different from the San Andreas? What does an intraplate rupture actually do to the ground beneath your feet, city by city, state by state? And what happens when the infrastructure that powers the eastern seaboard collapses into a sea of liquid sand? Stay with us. The answers will surprise you. Before we uncover the terrifying mechanics of the new Madrid seismic zone, make sure to subscribe to the channel. You will not want to miss a single chapter of this investigation. The human brain is wired to fear what it can see. When we consider catastrophic seismic threats to the United States, our collective anxiety immediately drifts to the West Coast. We picture the San Andreas Fault. It is a cultural icon of destruction. It is a visible, jagged scar tearing across the California landscape, actively monitored by thousands of surface sensors, satellite lasers, and GPS arrays. We know it is there. We can watch the Earth physically warp. But the most consequential seismic threat to the North American continent does not offer us the luxury of visibility. It is completely blind. It is structurally anomalous, and it is located entirely in the wrong place. Buried deep beneath the flat, agricultural heartland of the United States lies the new Madrid seismic zone. This is not the edge of a tectonic plate grinding against another. It is a deeply buried intraplate fault system, a fractured weakness sitting directly in the middle of the North American plate. It stretches for roughly 150 miles, diagonally crossing 5 states and holding 8 states within its immediate blast radius. Over 11 million Americans live directly above it. Yet, if you stand in a field in Missouri, Tennessee, or Arkansas, you will see no evidence of its existence. There are no jagged mountains, there are no surface ruptures, there is only flat, seemingly stable ground. This is the impossible fact of the new Madrid seismic zone. The mechanism that makes it so deadly is the exact same mechanism that makes it invisible. For millions of years, the Mississippi River and its tributaries have acted as a massive geological conveyor belt. They have relentlessly deposited layer upon layer of alluvial sediment, sand, gravel, and wet river mud, over the center of the continent. This sediment is not measured in feet, it is measured in miles. The actual tectonic bedrock where the new Madrid fault system operates is buried beneath a suffocating blanket of this ancient river dirt. Because of this profound depth, the standard tools of modern seismology are effectively blinded. We cannot easily track the creeping strain on the surface. We cannot measure the mounting tectonic friction. The fault system operates as a silent, rigid pressure cooker, accumulating immense kinetic energy in total darkness. The San Andreas bends. The San Andreas slips. The new Madrid simply waits. And when that pressure finally exceeds the tensile strength of the deep continental bedrock, it does not release as a gentle creeping shift, it detonates. To understand the scale of the threat, you must first understand the architecture of the trap. When tectonic plates collide on the west coast, they leave a physical signature. The earth buckles, mountains are thrust upward. Valleys are ripped open. But the new Madrid seismic zone operates under a fundamentally different set of physical laws. It does not scar the surface, it haunts the subsurface. The primary fault zone is a massive subterranean diagonal slash. It begins deep in northeastern Arkansas, near the small town of Marked Tree. From there, it tears northeast, carving directly through the Missouri Bootheel, crossing beneath the twisting channels of the Mississippi River, and extending into the borders of western Tennessee and western Kentucky. It finally terminates near the confluence of the Ohio and Mississippi rivers at Cairo, Illinois. That is 150 miles of highly volatile, fractured continental crust. It is buried. It is silent. It is immense. This entire 150-mile corridor sits squarely inside a region geologists call the Mississippi Embayment. In academic terms, the embayment is a broad, south-plunging syncline. In practical terms, it is a colossal geological trough, a subterranean bathtub stretching from Illinois all the way down to the Gulf of Mexico, carved deep into the ancient bedrock of the continent. For tens of millions of years, the Mississippi River has acted as a relentless conveyor belt. It has slowly filled this massive bathtub with alluvial sediment. This is not a thin layer of topsoil. This is a sedimentary wedge composed of loose sand, gravel, and water-saturated clay that reaches depths of up to 3,000 feet. That is more than half a mile of wet, unconsolidated mud stacked directly on top of the tectonic bedrock. This thick blanket of sediment dictates the terrifying geography of the fault. If you take a sledgehammer and strike the concrete bottom of a swimming pool filled with mud, you will not see the resulting crack in the concrete, but you will watch the surface of the mud violently heave. The new Madrid is the crack in the concrete. The American Midwest is the mud. Because of this profound obscuring layer, the precise boundaries of the fault system are inferred rather than visually observed. Modern seismologists must map the monster not by looking at the ground, but by listening to the micro-quakes echoing from the abyss. Through this deep acoustic mapping, they have identified a jagged, zigzagging network of subterranean fractures, 3 distinct interlocking fault segments that operate as a single, unified mechanism. The geography of this specific region built the American empire. The deep, rich soils created an agricultural superpower. The winding, navigable rivers created the ultimate logistical superhighway. But the subterranean geology tells a much darker story. The very river basin that brought life, infrastructure, and commerce to the heartland is the exact same mechanism actively masking its destruction. The structural foundation of this modern disaster was not formed recently, but over 750 million years ago. The American Midwest is fundamentally broken, and it has been broken since before the existence of complex life on Earth. To understand why the center of the continent is capable of catastrophic failure, we have to look past the mud, past the rivers, and directly into the crystalline basement rock. Geologists call this feature the real-foot rift. In the simplest terms, it is a 750-million-year-old tectonic scar. Hundreds of millions of years ago, an ancient supercontinent known as Rodinia began to tear itself apart. Tectonic forces pulled violently at the massive landmass. The continental crust stretched. It thinned. It fractured. Deep in what would eventually become the North American plate, a massive trench began to open, measuring approximately 40 miles wide and over 200 miles long. Geologists refer to this specific type of formation as a graben or an oligocene. That is the academic jargon. But the reality is far more visceral. Imagine a zipper running up the center of a heavy jacket. If you pull both sides of the jacket violently in opposite directions, the zipper splits and the material in the middle drops down. The real foot rift is that dropped material. It is a failed rift. The continent tried to rip itself entirely in half, but the tectonic engine driving the separation abruptly stalled. The zipper stopped halfway. The landmass did not fully divide, but the structural damage was permanently done. A colossal, jagged valley was left buried deep within the crust. The faults bordering this trench are immense, featuring massive subterranean cliffs with more than 10,000 feet of vertical displacement. Over the ensuing eons, this abyssal trench was buried under as much as 8 kilometers of dense rock and sediment. It vanished from the surface, but the scar never healed. It never fused back together. It remained a profound structural weakness hiding in the dark. This ancient failure is the exact mechanism that allows the new Madrid seismic zone to exist. The Earth's crust in this specific region is thinner, it is weaker, and it is compromised. The real foot rift acts as a pre-existing fault architecture, a perfectly designed subterranean channel waiting to be reactivated. It is silent. It is waiting. It is inevitable. To understand why the new Madrid seismic zone is uniquely terrifying, we must confront a fundamental division in geology: the difference between an interplate fault and an intraplate fault. The mechanics of an interplate fault are relatively straightforward. The San Andreas is an interplate boundary. It is the active grinding seam where 2 massive tectonic plates, the Pacific and the North American, are constantly sliding past one another. The friction is perpetual. The surface deformation is plainly visible. Because these plates are in continuous motion, the built-up stress is relieved frequently through a steady sequence of smaller earthquakes. It is a geological engine that constantly vents its pressure, but the new Madrid seismic zone operates under a far more insidious set of physical laws. Recent research confirms that the mechanics of intraplate earthquakes, those occurring deep within the interior of a tectonic plate, require a significantly more complex model than the activity seen at plate boundaries. The new Madrid is an intraplate fault system. It is completely landlocked within the rigid, unbroken expanse of the North American plate. Because it is not situated at the active edge of a tectonic plate, there is no constant large-scale grinding. In fact, modern GPS data mapping the surface deformation of the central United States reveals that present-day motion across the fault zone is virtually indistinguishable from zero. The surface movement is less than 0.2 millimeters per year, which equates to roughly the thickness of a piece of fishing line. This lack of visible surface deformation lulls the public into a false sense of security. But structural geologists understand the terrifying reality of the data. The absence of surface movement does not mean an absence of tectonic stress. It means the system is perfectly locked. Instead of venting pressure through frequent small tremors, the rigid bedrock of the mid-continent acts as a massive, unyielding elastic sponge. The tremendous tectonic forces pushing on the distant edges of the North American plate transmit stress thousands of miles inward, directly into the heart of the country. Because the crust here is ancient, cold, and immensely dense, it does not bend easily. It absorbs. This vast amount of kinetic energy is stored elastically within the deep rock. It accumulates in total silence. It builds for centuries, completely hidden beneath the miles of thick Mississippi River mud. The fault system operates as a silent, rigid pressure cooker. Over time, the accumulation of elastic strain on this specific intraplate segment relentlessly mounts until it inevitably exceeds the colossal frictional strength holding the ancient wheelfoot rift together. When that critical threshold is crossed, there is no gradual yielding. The accumulated elastic strain is released in a catastrophic, instantaneous rupture. The pressure cooker explodes, the trapped kinetic energy detonates outward, forcing the deep continental crust to violently snap back into place. This is the grim reality of intraplate mechanics. The longer the silence, the greater the violence. To understand the maximum destructive ceiling of the new Madrid seismic zone, we do not need to rely on abstract computer models. We simply need to look at the historical record. The structural integrity of this intraplate zone has failed before. It failed catastrophically in the winter of 1811, and the geological violence it unleashed remains entirely anomalous in the recorded history of the North American continent. On December 16, 1811, at roughly 2:15 in the morning, the deep bedrock beneath northeastern Arkansas abruptly snapped. The stored kinetic energy of centuries was released in a single, terrifying instant. Geologists quantify this release using moment magnitude, a measurement of the total energy expended during a quake. By analyzing the macroseismic effects, the physical footprint of the damage left behind, researchers estimate this initial shock was a staggering 7.7 magnitude event. It was not a solitary rupture. It was an awakening. At 7:15 that same morning, a massive aftershock ripped through the region. 5 weeks later, on January 23, 1812, a second principal main shock, estimated at a magnitude 7.5, struck the Missouri Bootheel. Finally, on February 7, a subterranean structure known as the Real Foot Blind Thrust detonated in a third primary earthquake that dwarfed the previous two. Geological estimates for this final catastrophic rupture range from a 7.4 to an unprecedented 8.8 magnitude, 3 massive main shocks, 3 distinct geological detonations, 1 continuous winter of structural failure. We must be intellectually honest about the data. Modern seismographs did not exist in the early 19th century. We do not possess precise instrumental recordings of the waveforms. The magnitudes assigned to the 1811 and 1812 sequence are forensic estimates, calculated retroactively by mapping the unprecedented distance the ground shaking traveled. But the sheer scale of that footprint is sobering. This was not a localized disaster. The shock waves from the December 16 rupture violently agitated the entire Mississippi River Valley. The kinetic transfer was so severe and so structurally pervasive that the vibrations traveled east and woke President James Madison in the White House, nearly 900 miles away. This sequence proves a fundamental, terrifying characteristic of the new Madrid system. When this intraplate fault fails, it does not release its energy in one clean break. It initiates a cascading failure. The initial rupture alters the regional tectonic stress field, instantly transferring immense pressure onto adjacent locked fault segments. It loads the neighboring springs until they too detonate. The winter of 1811 proved the ceiling of this invisible monster. The fault is fundamentally capable of producing not just a single major earthquake, but a relentless sequence of overlapping mega-quakes spanning months. The written accounts from the 1811 and 1812 sequence do not describe an earthquake in the traditional sense. They describe the total structural failure of the solid Earth. When modern Americans envision an earthquake, they picture intense, violent shaking. Books fall off shelves, drywall cracks, unsecured foundations slip. But the historical accounts from the Mississippi River Valley detail a phenomenon that is far more terrifying to comprehend. The ground temporarily ceased to be solid, because the new Madrid seismic zone sits beneath a massive sedimentary basin of wet river mud and sand. The extreme kinetic energy of the ruptures triggered massive, widespread soil liquefaction. The intense vibration compacted the loose soil, exponentially increasing the pressure on the water trapped between the individual grains of sand and clay. In an instant, the water pressure effectively superseded the friction holding the dirt together. The ground literally became a fluid. Eyewitnesses, including the renowned ornithologist John James Audubon, who was riding horseback in Kentucky during the quakes, documented this unimaginable horror. He described the ground rising and falling like the ruffled water of a lake. This was not a metaphorical exaggeration. The combination of complete soil liquefaction and immensely powerful seismic shear waves caused the surface of the Earth to physically undulate. Solid ground rolled in visible kinetic waves, ripping across the landscape with crests reported to be 3 feet high. Imagine standing in a dense, old-growth forest. Now imagine the forest floor rolling like the swells of the open ocean. As these massive, undulating waves of earth passed through the timber, the root systems were violently pitched back and forth. The sheer kinetic torque was so extreme that massive, ancient trees simply snapped in two as they were whipped back and forth. Witnesses watched entire forests physically tear themselves apart, the deafening cracks of breaking timber mixing with the subterranean roar of the rupturing fault. And the horror was not confined to the surface waves. The immense subterranean hydraulic pressure had to escape. In thousands of locations, the pressurized, liquefied slurry of the subsurface violently breached the topsoil. Witnesses described massive geysers of sand, water, and deep earth coal violently exploding high into the air. One settler documented an inescapable terror where the surface sank, and a mysterious black liquid began rapidly rising to the belly of his terrified horse. These were sand blows or sand volcanoes, massive eruptions of subterranean fluid that left behind acres of toxic sulfuric mud and crater-like cones. The earth did not just shake, it boiled, it rolled, it drowned the surface from below. The most terrifying visual from the winter of 1811 is not the falling timber, it is the behavior of the continent's greatest river. On February 7, 1812, at approximately 3:45 in the morning, the third and most violent main shock detonated. This rupture did not just shake the earth, it fundamentally altered the topography of the riverbed. A deeply buried tectonic structure known as the Reelfoot Fault violently failed. This specific structure is a thrust fault. Thrust faults do not merely slide side to side, they push the crust violently upward. In a matter of seconds, the tectonic engine drove a massive slab of bedrock toward the surface. This created a geological feature called a fault scarp, a literal physical step in the earth. This step did not happen in an empty field. It happened directly underneath the Mississippi River. Imagine a massive, invisible hydraulic press suddenly lifting the bottom of a flowing aqueduct. The sheer kinetic force of the upthrust created a physical blockade across the channel of the Mississippi. The river was instantly choked. The immediate result was an event so structurally anomalous that modern science initially struggled to believe the historical accounts. The Mississippi River flowed backward. The sudden uplift of the riverbed, combined with the profound dropping of the land just to the north, forced millions of gallons of moving water to violently reverse course. The immense kinetic energy of the rupture also generated what geologists call a fluvial tsunami, a massive northward-moving wave of water tearing upstream against the natural current. Eyewitnesses on unpowered flatboats, completely exposed to the elements, watched in horror as the water changed from a steady current to a churning, rusty brown slurry. It grew thick with toxic mud, submerged sediment, and violently uprooted debris. The sheer hydraulic turbulence stripped the riverbanks of their ancient forests, sending massive, dead trees rocketing up from the bottom of the riverbed like ballistic missiles. The water had to go somewhere. The structural uplift to the south acted as a wall. The subsidence to the north acted as a drain. The river breached its banks, pouring backward into the newly sunken land and submerging entire forests. It created temporary waterfalls. It completely destroyed the town of New Madrid. The Mississippi River is the heaviest, most powerful hydraulic force on the North American continent. On February 7, 1812, the subterranean monster of the mid-continent stopped it, turned it around, and used it to erase the map. The immediate consequence of the February 7 rupture was not just the temporary reversal of the Mississippi River, it was the permanent, violent alteration of the North American map. When the subterranean Reelfoot Fault shoved a massive block of bedrock upward, physics demanded an equal and opposite reaction. As the land to the south violently rose to form what geologists now call the Tiptonville Dome, the Earth immediately to the north collapsed. This is a geological process known as subsidence. But in the winter of 1812, this was not a gradual settling of topsoil. It was a sudden, catastrophic structural failure of the crust. Over an area spanning tens of thousands of acres in northwestern Tennessee, the ground simply dropped out from under the dense, old-growth forest. Eyewitnesses and subsequent geological surveys confirmed that the surface elevation plummeted anywhere from 5 to 20 feet in a matter of minutes. To put that in perspective, imagine standing on the roof of a two-story house, and in the span of a single violent tremor, your roof drops to the level of the front lawn. Now apply that exact scale of vertical collapse to an entire regional landscape. The immediate result was a massive, newly formed topographic bowl. And because the Mississippi River had just been physically dammed by the tectonic uplift to the south, the reversed river had found its drain. Millions of gallons of churning, debris-filled water violently breached the riverbanks and poured directly into this new geological depression. The floodwaters did not merely fill a hole, they drowned a living ecosystem. Within hours, an entire ancient forest of massive cypress and pecan trees was completely submerged in deep, muddy water. The sheer volume of the inundation created a brand new inland body of water that had never previously existed. We call it Reelfoot Lake. Today, Reelfoot Lake remains a massive flooded scar on the landscape of Tennessee. It is not a natural glacial lake. It is a tectonic crater. If you take a boat out on the water today, you can still see the ghostly, jagged stumps of the drowned cypress trees sitting just below the surface, a perfectly preserved, 200-year-old graveyard of the forest that was dragged down into the earth. The birth of Reelfoot Lake is the ultimate, terrifying proof of the New Madrid's power. It demonstrates that this specific fault system does not just shake buildings, it reshapes the continent, it dictates where rivers flow, it erases solid land. The scale of a catastrophic event is usually measured by the devastation at its epicenter. But the true, systemic terror of the New Madrid seismic zone is not localized. It is continental. When the San Andreas Fault slips in California, the resulting damage is undeniably severe, but it is relatively contained. The mechanism dictating this containment is a concept seismologists call seismic attenuation, the rate at which ground motion decreases as it travels away from the source. Because the active crust on the west coast is heavily fractured, significantly warmer, and pulverized by millions of years of continuous tectonic grinding, seismic waves rapidly lose their kinetic energy. It simply dies. It is like trying to ring a bell made of cracked, warm clay. The acoustic vibration cannot travel. The bedrock of the central United States, however, is structurally anomalous. It does not absorb kinetic energy. It broadcasts it. During the winter of 1811 and 1812, the immense energy unleashed by the New Madrid ruptures did not stay confined to the Mississippi River Valley. It traveled outward in a devastating unbroken wave. Because the deep continental crust of the North American plate is incredibly ancient, cold, and entirely intact, it acted as a colossal, subterranean amplifier. The physical footprint of the 1811 sequence remains sobering to comprehend. The ground shaking was not just felt in neighboring counties. It traveled nearly 1,000 miles east and physically rang the heavy bronze church bells in Boston, Massachusetts. It radiated north, rattling the foundations of structures in Montreal, Canada. It surged toward the Atlantic, waking President James Madison in the White House in Washington, D.C. This was not a slight, imperceptible tremor on the edge of human awareness. This was a sustained, structural vibration capable of knocking down masonry chimneys in Cincinnati, Ohio, over 350 miles away from the initial epicenter. Modern geological data confirm the terrifying math behind these historical accounts. Because of the sheer density and unbroken architecture of the mid-continent bedrock, a rupture on the New Madrid seismic zone shakes an area approximately 20 times larger than an earthquake of the exact same magnitude on the west coast. 20 times the geographical impact, 20 times the structural exposure, 20 times the population at risk. The west coast relies on an assumption of containment. The Midwest relies on an architecture of broadcast. When the New Madrid fails, it does not just destroy the epicenter, it shakes the very edges of the American empire. To comprehend why a regional earthquake can physically rock half a continent, we must look at the deep architecture of the North American plate. The ground beneath California and the ground beneath the Midwest do not simply look different on the surface. They obey fundamentally different acoustic and kinetic laws deep underground. Geologists refer to the foundational bedrock of the central and eastern United States as the North American craton. This is not just rock. It is the ancient, unyielding anchor of the continent. When we examine the crust on the west coast, we are looking at a geological infant. It is young, incredibly hot, and profoundly shattered. Millions of years of relentless tectonic collisions have pulverized the bedrock. Magma chambers and geothermal activity keep the subsurface temperatures remarkably high, fundamentally altering the strength of the crust. When a fault ruptures in California, the resulting kinetic energy is forced to travel through this hot, highly fractured medium. The physical result is rapid seismic attenuation. The shattered, warm crust acts like a massive acoustic shock absorber. It absorbs the energy, scattering the waves and bleeding off their destructive power over a relatively short distance. Striking the San Andreas is like striking a cracked bell made of warm clay. The sound dies almost immediately. But the North American craton is structurally opposite in every measurable way. The bedrock beneath the Midwest is astonishingly old. Portions of this craton were forged between 1 and 4 billion years ago. Because it has sat isolated from the active grinding edges of the tectonic plates for hundreds of millions of years, the rock has been allowed to aggressively cool. It is ancient, it is frigid, it is unbroken. This extreme age and low temperature create an environment of tremendous density. In seismology, the efficiency with which a material transmits energy is often quantified by its Q factor, or quality factor. A high Q factor signifies low attenuation, meaning the kinetic energy does not easily bleed away into the surrounding Earth. The fractured, warm crust of California has a remarkably low Q factor, typically measuring between 80 and 250. The frigid, dense craton of the central and eastern continent possesses an exponentially higher Q factor, frequently measuring between 700 and 1,000. When the New Madrid seismic zone detonates, it is not striking a cracked bell. It is striking a massive, perfectly cast anvil of solid iron. Because the craton is so cold, so dense, and so structurally unified, it lacks the microscopic fractures necessary to absorb and scatter the seismic shear waves. The kinetic energy does not dissipate. It is forced to travel horizontally, rocketing through the unbroken basement rock at terrifying speeds. The bedrock acts as a highly efficient continental conduit, preserving the destructive amplitude of the waves as they race outward from the Mississippi River Valley. This is the hidden anatomy of the American heartland. The very density that makes the craton so historically stable is the exact physical property that guarantees its structural broadcast. The cold, dense craton explains how the seismic energy travels such immense distances, but it does not fully explain why the surface shaking in the Midwest is so violently exaggerated. To understand the localized destruction, we must look at the specific intersection of the hard bedrock and the soft mud. Seismologists refer to this intersection as the Basin effect. The instrument requires two distinct physical components to produce its thunderous sound: a rigid, unyielding frame and a flexible, stretched skin. The North American craton is the rigid frame. The Mississippi embayment, the 3,000 feet of wet, unconsolidated sediment, is the skin. When the new Madrid fault ruptures deep within the craton, the sheer kinetic energy races upward through the solid rock at terrifying speeds. But when those high-velocity seismic shear waves hit the bottom of the sedimentary basin, they encounter a profound shift in physical medium. The waves are instantly transitioning from dense, hard rock into soft, slow dirt. In acoustics and seismology, this transition is governed by a principle known as acoustic impedance. Because the velocity of the seismic wave abruptly drops as it enters the soft mud, the physical amplitude of the wave must drastically increase to conserve the total kinetic energy. The Earth does not just shake, it whips. Furthermore, the immense contrast in density between the hard bedrock and the soft mud creates a subterranean mirror. As the amplified seismic waves travel up to the surface, they hit the open air and reflect back down. When they reach the bottom of the mud and strike the hard bedrock, they reflect back up. The kinetic energy becomes trapped within the sediment. It reverberates, it bounces, it echoes. This is the literal bass drum effect. On the west coast, the pulverized crust absorbs the energy of a rupture, and the most violent shaking typically lasts for 10 to 20 terrifying seconds. But in the Mississippi embayment, the trapped kinetic energy continues to resonate through the sediment basin long after the deep fault has stopped moving. The deep mud simply continues to ring. A magnitude 7.7 event in this geological bathtub does not just create a larger geographic footprint, it creates an exponentially longer duration of structural stress. The ground does not merely vibrate, it rolls. It sustains a violent, mechanical resonance that modern human infrastructure was fundamentally never engineered to survive. To understand the localized devastation of a new Madrid rupture, we must examine the skin of the bass drum. We must look at the exact composition of the ground directly beneath the foundations of the American heartland. The Mississippi embayment is not a shallow valley. It is a massive, south-plunging geological trough filled over tens of millions of years with an immense wedge of loose sediment. For over 70 million years, the ancestral Mississippi River and a prehistoric, encroaching ocean have acted as relentless depositional engines. They poured thousands of cubic miles of marine clay, terrestrial gravel, and fine river silt into the ancient trough of the Real Foot Rift. This continuous dumping created what geologists classify as a sequence of late Cretaceous, Tertiary, and modern Quaternary alluvium. In practical terms, it is a staggering accumulation of river gravel, loose sand, and deep clay. In some areas, this unconsolidated sedimentary layer reaches depths of roughly 3,000 feet before finally hitting the solid rock of the craton. This material has not been subjected to the immense subterranean heat and pressure required to lithify it, to fuse it into solid stone. It is not solid rock. It is not structurally cohesive. It is an ocean. The defining catastrophic characteristic of this alluvial basin is its hydrology. Because it is the active floodplain of the continent's largest river system, the regional water table sits alarmingly close to the surface. The deep, microscopic voids between the individual grains of sand, silt, and clay are not filled with air. They are completely saturated with groundwater. The entire mid-continent is resting on a massive, waterlogged sponge. This creates a profound structural vulnerability. When you construct a heavy, rigid object, a historic brick building, a high-voltage steel transmission tower, or the concrete pylons of an interstate overpass, on top of this material, you are fundamentally relying on the microscopic friction between the grains of dirt to hold that immense weight. Under normal static conditions, gravity ensures that this friction is sufficient. The soil particles bear the load, the dirt holds, the foundation rests securely. But an earthquake does not obey static conditions. Modern infrastructure demands absolute rigidity. The massive suspension bridges crossing the Mississippi River at Memphis and St. Louis require immovable anchors. The heavy, unreinforced masonry that characterizes downtown districts throughout the Midwest demands a foundation that will not yield. The quaternary alluvium of the Mississippi embayment cannot provide that rigidity. It is structurally unsuited to withstand sustained kinetic vibration. When the extreme, amplified kinetic energy from the deep craton hits this unconsolidated sedimentary wedge, the physical rules governing friction abruptly fail. The violent, sustained resonance of the trapped shear waves physically compresses the loose soil. It violently shakes the grains of sand together, and because those grains are completely surrounded by trapped, pressurized groundwater, the geological architecture of the Midwest is primed for a sudden, catastrophic phase change. When the immense, reverberating kinetic energy from a new Madrid rupture hits the saturated alluvial soils of the Mississippi Basin, it triggers a devastating geotechnical phenomenon known as soil liquefaction. In the simplest terms, the solid ground temporarily loses its structural integrity and behaves entirely like a liquid. It is not a gradual settling, it is a sudden, catastrophic phase change. The physics behind this transformation are unforgiving. The deep, loose sediments beneath the Midwest are completely saturated. The microscopic voids between individual grains of sand and silt are filled with groundwater. Geologists refer to this trapped fluid as pore water. Under normal static conditions, the grains of dirt rest physically against one another in edge-to-edge contact. This microscopic friction bears the immense weight of the buildings, roads, and bridges constructed above. The water simply sits passively in the gaps, but an earthquake violently disturbs this structural arrangement. The sustained, rolling shear waves of a new Madrid event physically compress the loose soil matrix, attempting to force the dirt particles into a denser, tighter formation. Because the water trapped in the pore spaces cannot drain fast enough through the sediment to accommodate this rapid compaction, the subterranean hydraulic pressure instantly spikes. This escalating pore water pressure pushes back against the dirt with immense force, eventually exceeding the static friction holding the earth together. In a matter of seconds, the water physically separates the soil grains. The dirt particles lose edge-to-edge contact and become entirely suspended in the pressurized water. The earth loses all cohesion. It loses its shear strength. It loses its bearing capacity. Solid ground is instantly converted into a deep, heavy liquid mush. The infrastructure built upon it reacts exactly as physics dictates. Objects heavier than the liquefied soil sink, while objects lighter than the soil violently float. The foundations of heavy brick buildings, hospitals, and high-rise apartments suddenly find themselves resting on a fluid bed, causing them to plunge downward into the earth like stones dropped into quicksand. Conversely, buoyant subterranean infrastructure, buried natural gas pipelines, massive septic tanks, and empty sewer mains are violently shoved to the surface, snapping their connections and bursting through the pavement. We have seen modern infrastructure meet this exact phenomenon. During the 2011 earthquakes in Christchurch, New Zealand, an event with a relatively modest magnitude of 6.2, widespread liquefaction caused the ground to simply open up, swallowing moving cars whole into the resulting muck. It destroyed 15,000 single-family homes. It devastated the central business district. It forced hundreds of thousands of tons of toxic silt to the surface, burying streets and gardens. Now, scale that localized disaster to the catastrophic sealing of the New Madrid Fault. The 1811 and 1812 sequence triggered massive soil liquefaction and ground failure over an astonishing area of roughly 6,000 square miles. This is not a localized structural failure. It is the sudden transformation of a multi-state region into an ocean of structural quicksand. The soil beneath the Midwest is fundamentally broken, but the true catastrophe of a new Madrid rupture is not strictly geological, it is architectural. The American heartland was built with an astonishing disregard for the monster sleeping beneath it. If you walk through downtown Los Angeles or San Francisco, you are walking through a fortress of modern seismic engineering. Because the West Coast experiences frequent tectonic grinding, its infrastructure is built on an assumption of violence. Buildings are constructed with flexible steel skeletons, massive concrete counterweights, and base isolators designed to decouple the structure from the shaking ground. California building codes are legally unforgiving. If a structure cannot bend, it cannot be built. The central United States operates under a terrifyingly different architectural philosophy. Because catastrophic intraplate ruptures happen on a timescale of centuries rather than decades, a profound complacency has dictated the construction of the region. Geological models imply a recurrence interval of 500 to 1,200 years for a major 7.0 to 8.0 magnitude event. Buildings generally have a useful lifespan of 50 to 100 years. Consequently, the vast majority of structures in the Midwest are built under the statistical assumption that they will never experience a significant earthquake. The result is a regional infrastructure dominated by the most seismically vulnerable material on the planet, unreinforced masonry. or URM. Unreinforced masonry is exactly what it sounds like. It is brick, cinder block or stone held together strictly by the chemical bond of brittle mortar, without any internal steel rebar or flexible reinforcement. It is the defining aesthetic of the American heartland. It is the historic brick storefronts lining the main streets of Missouri. It is the aging mid-century schools of Tennessee. It is the heavy, ornate churches of Arkansas. Memphis and St. Louis alone house millions of people in these unreinforced masonry structures. In Shelby County, Tennessee, which encompasses Memphis, structural analyses reveal thousands of critical, aging facilities constructed of URM, including numerous public schools built over half a century ago. This architectural legacy is a structural death sentence during a massive shear wave event. When a seismically engineered building in California is hit by a kinetic wave, the steel rebar hidden inside the concrete allows the building to flex. It absorbs the kinetic energy, warping without snapping. Unreinforced masonry cannot flex. It possesses immense compressive strength. It can hold a massive amount of weight pushing straight down. When the prolonged, rolling vibrations of the new Madrid bass drum hit a brick building, the walls are suddenly forced to move horizontally. The rigid mortar instantly shatters. Without a steel skeleton to hold the heavy bricks together, the entire structure completely loses its integrity. The building does not slowly collapse. It explosively unzips, heavy brick facades shear off and plummet into the streets below. Roofs, no longer supported by load-bearing walls, pancake downward, crushing everything inside. Even during the 1811 sequence, when the region was incredibly sparsely populated, the minimal unreinforced masonry that did exist, like the stone chimneys and solid stone buildings 150 miles away in St. Louis, suffered heavy damage, breaking and collapsing from the sustained vibration. Today, those exact vulnerable architectural methods make up the backbone of entire metropolitan skylines. We have placed our heaviest, most rigid, and most brittle buildings directly on top of the deepest, wettest, and most unstable soil in the country. The geometry of this disaster has a distinct focal point. It is not an empty agricultural field in the Missouri Bootheel. It is a dense, critical metropolitan center of over 1 million people. It is Memphis, Tennessee. When we superimpose the geological maps of the Mississippi embayment over the population density of the mid-continent, a terrifying alignment emerges. Memphis sits directly within the crosshairs of the new Madrid seismic zone. More importantly, the city was built squarely on top of the deep, waterlogged alluvial soils that characterize the region. The nature of these specific geologic materials dictates the terrifying severity of the damage that the city's infrastructure will sustain. If a 7.7 magnitude rupture detonates today, Memphis will not merely experience a natural disaster, it will experience a sudden, systemic structural failure. The initial threat is from below. Because the city rests on loose, saturated sediment, it is situated in a zone of extreme liquefaction probability. When the amplified shear waves arrive, the groundwater pressure beneath Shelby County will equalize with the soil grains. The ground beneath the roads, the commercial districts, and the residential neighborhoods will temporarily flow like a fluid. Deep fissures will violently open, tearing apart pavement, while pressurized mud and sand erupt onto the surface. But the true, catastrophic vulnerability lies above ground. Memphis was historically not built to withstand the kinetic energy of a massive intraplate earthquake. Very few buildings in the metropolitan area were constructed using modern building codes, with rigorous seismic-resistant designs. Because catastrophic earthquakes happen so infrequently in this region, the city is defined by an aging infrastructure characterized by immense amounts of unreinforced masonry and rigid tilt-up concrete. This is not a vulnerability isolated to abandoned factories or historic storefronts. Structural surveys reveal a sobering reality. A terrifying percentage of the city's essential facilities rely precisely on this brittle architecture. Unreinforced masonry is the most common type of construction for the region's essential operations. When the deep bedrock snaps, the very buildings designed to coordinate the emergency response will be among the first to structurally fail. Police stations will shatter, fire stations will structurally compromise. Public schools, constructed of heavy, rigid, unreinforced brick, possess virtually zero tensile strength against the sustained horizontal vibration of the trapped seismic waves. Because of the remarkably low regional attenuation in the Midwest, The seismic waves will not simply strike Memphis and quickly fade. They will trap themselves in the deep sediment under the city, doing catastrophic damage over an unnaturally long duration. The heavy brick facades will shear off into the streets. The liquefied soil will consume the foundational supports. The dense urban population will immediately find itself trapped in a city where the infrastructure has fundamentally turned against them. The disaster is mathematically inevitable. The architecture is unforgiving. The ground itself is the weapon. Memphis is the epicenter, but it is not an isolated casualty. The true nightmare of the new Madrid seismic zone is the sheer geographic scale of its destructive footprint. When a hurricane strikes the Gulf Coast or a major earthquake shakes Los Angeles, the disaster is localized. The surrounding states remain fully functional, able to funnel massive amounts of federal aid, heavy equipment, and medical personnel directly into the impact zone. The cavalry can stage at the borders and rush in. A new Madrid rupture fundamentally eliminates the borders. The amplified shear waves will travel violently outward through the cold, dense craton, instantly turning a localized disaster into a synchronized multi-state catastrophe. As the shock waves race north up the Mississippi River corridor, they will strike St. Louis, Missouri. St. Louis sits roughly 150 miles from the primary fault zone, a distance that would historically guarantee safety on the west coast. But because of the craton's incredibly low seismic attenuation, the kinetic energy will arrive largely intact. The metropolitan area relies heavily on the exact same brittle historic architecture that dooms Memphis: unreinforced brick masonry. We already have the empirical proof of this vulnerability. In 1968, a moderate 5.5 magnitude earthquake struck southern Illinois. Even at that relatively minor intensity, the kinetic energy traveled over 100 miles and successfully toppled chimneys and fractured brick facades throughout the St. Louis area. A 7.7 magnitude event would release over 1,000 times more kinetic energy. It would subject the aging infrastructure of St. Louis to sustained, rolling vibrations capable of pancaking unprotected masonry and compromising critical infrastructure. Simultaneously, the southern segment of the fault will project immense kinetic energy toward Little Rock, Arkansas. The shock waves will tear through the state's commercial center, triggering localized structural failures and shattering unreinforced foundations. In a matter of minutes, multiple major metropolitan centers will structurally fail at the exact same time. This presents a scenario that completely paralyzes the standard operational playbook of the Federal Emergency Management Agency. In 2011, FEMA and the Central United States Earthquake Consortium conducted a massive, national-level simulation of a 7.7 magnitude new Madrid rupture. The data from this exercise, officially designated NLE-11, revealed a staggering logistical impossibility. The disaster directly impacts 8 states simultaneously. Over 44 million people live in this broader 8-state region, with roughly 12 million residing in the highest risk zones. When the Earth stops shaking, there will be no functional staging areas on the immediate periphery. First responders in Illinois cannot rush to help Tennessee because Illinois will be actively pulling its own citizens from the rubble. The command centers, the emergency medical transport hubs, and the communication arrays across half the continent will be destroyed or severely compromised all at once. This is the grim reality of a mid-continent rupture. The federal government will not be responding to a single, contained disaster. It will be forced to wage an unwinnable logistical war across 8 concurrent operational theaters. When you look at a topographical map of the United States, the Mississippi River is not simply a body of water. It is a massive geographic wall that physically divides the eastern half of the continent from the west. The only way to move the colossal volume of American commerce, military assets, and emergency resources across this natural divide is through a shockingly fragile network of steel bridges. These massive structures are the vital circulatory arteries of the national supply chain. If a 7.7 magnitude intraplate rupture detonates along the new Madrid seismic zone, the structural failure of these critical river crossings will instantly and physically bisect the United States. The geographic alignment is unforgiving. The primary fault zone runs directly parallel to and frequently crosses beneath the Mississippi River itself. This means the very bridges required to connect the country are sitting directly at ground zero. Consider the Hernando de Soto Bridge in Memphis. It is a massive, arching steel structure that carries Interstate 40, one of the most critical east-west freight corridors in the nation, directly across the river. When it was constructed in the early 1970s, it was built with virtually no seismic protection. While state transportation departments have spent recent decades attempting to retrofit this specific structure with friction pendulum isolation bearings, the structural reality of the entire region remains intensely sobering. A bridge is only as strong as the earth holding it up. Even if the reinforced steel spans of a modernized bridge manage to survive the immense sustained kinetic whipping of the craton, the surrounding geography will not. The massive approach ramps, the connecting interstates, and the immense concrete pylons rest precisely on the deep, unconsolidated alluvial sediment of the Mississippi Basin. When that sediment undergoes catastrophic soil liquefaction, the ground supporting the highways leading to the bridges will simply turn to liquid sand. The bridges will become useless steel islands surrounded by impassable liquefied mud. Federal emergency planners understand this exact terrifying bottleneck. During the massive National Level Exercise 11 on LE-1, a catastrophic simulation modeling a 7.7 magnitude New Madrid rupture, FEMA and the Department of Defense recognized that the destruction of transportation lifelines would immediately paralyze their ability to move resources. The simulation projected widespread, multi-state damage to the critical infrastructure crisscrossing the river. Without these bridges, there is no detouring. If you lose the crossings at Memphis and St. Louis, long-haul trucking cannot simply take the next exit. Hundreds of thousands of commercial vehicles transporting food, medical supplies, and industrial components will hit a sudden, impassable geographic wall. The unbroken flow of the American economy relies on continuous, rapid transit. A massive mid-continent rupture will not just pause this transit, it will shatter the concrete arteries required to sustain it. The bridges are not the only vital arteries crossing the Mississippi embayment. Above the ground, suspended in the air, sits the most critical vulnerability of the modern era, the electrical transmission network. The central United States is powered by a massive backbone transmission system. These are not your neighborhood wooden utility poles. These are colossal steel structures carrying massive high-voltage lines ranging from 345 to 750 kilovolts, directly linking states across the Midwest and the South. They are the critical high-capacity veins of the American electrical grid, and they are built upon a fatal geotechnical assumption. The towering steel structures that carry these high-voltage lines rely on what structural engineers call isolated footings. Because a standard transmission tower has 4 legs, each leg is anchored into its own independent buried concrete pad. This design works perfectly when the soil beneath all 4 pads remains equally solid and stable. But a 7.7 magnitude New Madrid rupture guarantees the exact opposite. When the deep alluvial sediment undergoes catastrophic liquefaction, it does not lose its structural integrity evenly. The ground effectively turns to thick soup. The isolated footings are no longer resting on solid earth. They are plunging into an ocean of pressurized, fluid sand. Because the 4 independent footings will inevitably sink at different rates into the liquefied mud, the towers will experience immediate, massive, asymmetrical settlement. Physics takes over. The immense center of gravity shifts. The tower inclines. The steel warps. Historical precedent proves this vulnerability. During the 1964 Niigata earthquake, transmission towers visibly leaned and partially collapsed simply because the ground beneath them liquefied and swallowed their foundations. In the American Midwest, the Department of Energy models project a staggering scale of structural failure. A simulated catastrophic New Madrid event estimates that between 170 and 200 massive high-voltage towers sit directly in the most violent liquefaction zones and are at extreme risk of total physical destruction. When a 500 kilovolt transmission tower collapses, it does not just fall over. It snaps the structural tension of the entire interconnected line. The kinetic shock of the collapsing towers, combined with the intense, sustained ground shaking, will instantly de-energize approximately 750 transmission lines and completely compromise up to 300 major substations near the epicenter. This cascading physical failure will abruptly disconnect roughly 11,300 megawatts of active electrical generation. The resulting blackout will not be a localized inconvenience. It will be a continental catastrophe. The Department of Energy simulation projects that the sudden, violent disruption of this central transmission hub will trigger cascading grid failures far beyond the immediate fault zone. Because the grid is entirely interconnected, The shockwave of this sudden voltage drop could rapidly expand across the Midwest, the Southeast, and the Northeast. Federal modeling suggests the resulting outages could impact between 100 and 150 million people. The power grid requires an unbroken circuit. The deep craton ensures a massive kinetic shock. The liquid soil guarantees the physical collapse. The bridges and the high-voltage lines sit visibly above the Earth, but the most economically lethal target of the new Madrid seismic zone is buried quietly beneath it, running directly through the deepest, most unstable alluvial soils of the Mississippi Basin is a massive, subterranean network of transcontinental pipelines. The American Midwest does not just grow the nation's food, it serves as the primary geographic funnel for its energy. Every day, immense volumes of crude oil and natural gas are pumped from the south to the refineries and populations of the Midwest and the northeastern United States. Consider the Capline pipeline. It is a massive, 40-inch diameter conduit constructed in 1968 from heavy welded steel pipe with rigid arc-welded joints. It is designed to move colossal amounts of crude oil straight through the exact geographic footprint of the new Madrid fault. Like many of the critical energy lifelines in this region, it was built decades before the mechanics of intraplate liquefaction were fully understood. These pipelines are deeply buried. They rely entirely on the surrounding Earth to keep them structurally supported, insulated, and safely concealed. But when a 7.7 magnitude rupture detonates, the Earth surrounding these pipelines will violently abandon them. Because these pipes are trenched directly within the floodplain of the Mississippi River, they sit squarely within the zones of highest liquefaction probability. When the amplified kinetic energy traps itself in the basin, the saturated sediment will suddenly turn into a heavy, pressurized liquid. Physics dictates a brutal consequence for buried infrastructure during this phase change. A hollow steel pipe filled with gas or oil is incredibly buoyant compared to an ocean of dense, liquefied mud. The pipe wants to float. The Earth wants to sink. The subterranean pressure will violently shove these massive, rigid steel conduits upward, while the heavy liquid soil simultaneously drags the surrounding terrain downward, subjecting the aging infrastructure to catastrophic shear forces. Furthermore, a phenomenon known as lateral spreading, where the liquefied ground physically slides sideways toward the river channels, will forcefully drag the buried pipes along with the moving Earth. Steel can bend, but older, rigid, arc-welded joints spanning a massive geological fault cannot survive a sudden, multi-directional geotechnical assault. The pipelines will snap. This failure will not be isolated to a single line. A major intraplate rupture guarantees the simultaneous snapping of multiple transcontinental energy arteries across the embayment. Highly pressurized natural gas will erupt outward. Millions of gallons of crude oil will bleed directly into the ruptured, shifting topography of the Mississippi River Valley. It is a subterranean catastrophe that instantly creates an unparalleled environmental nightmare, while simultaneously severing the physical energy lifeblood of the eastern half of the continent. The east coast of the United States operates under a terrifying illusion of energy independence. The towering skyscrapers of New York City, the dense manufacturing hubs of Pennsylvania, and the sprawling suburbs of the Mid-Atlantic project an image of immense power, but they do not produce the energy required to sustain it. They import it. The eastern seaboard is geographically starved for petroleum and natural gas refining capacity. It relies almost entirely on a massive subterranean circulatory system that pumps fuel continuously from the Gulf Coast and the southern plains directly to the northeast, and the major arteries of that system are buried precisely in the kill zone. Consider the Colonial Pipeline. It is the largest refined petroleum products pipeline by volume in the country. Every single day, it transports roughly 100 million gallons of fuel across a 5,500-mile network, acting as the primary energy umbilical cord for the East Coast. It is responsible for delivering nearly 45% of all the fuel consumed on the eastern seaboard. Or consider the Transcontinental Gas Pipeline, known as Transco. This massive system is the largest natural gas pipeline in the United States, transporting approximately 20% of the nation's entire natural gas supply from South Texas straight into the heart of New York City. These are not redundant systems. They are singular, irreplaceable bottlenecks, because the Gulf Coast is the primary refining engine. These massive pipelines must physically cross the deep, vulnerable geology of the Mississippi embayment and the broader southern periphery of the North American craton to reach the northeast. When the subterranean bedrock snaps and the massive alluvial basin turns to fluid, the ensuing pipeline ruptures will trigger a sudden cascading energy starvation event thousands of miles away. The timeline of this collapse is unforgiving. If a 7.7 magnitude intraplate rupture severs the major natural gas and petroleum pipelines in the Midwest and Mid-South, the East Coast does not have months of strategic reserves to fall back on. The pressure drops immediately. The flow stops. The taps run dry. Within 48 hours, the absence of jet fuel will ground commercial aviation across the eastern seaboard. Within 72 hours, the localized gasoline reserves at civilian filling stations will be entirely depleted, paralyzing commuter traffic, halting delivery trucks, and severely degrading local emergency services. But the true, existential threat is the sudden loss of natural gas. The Northeast relies heavily on continuous natural gas delivery to power its electrical generation plants and to provide direct thermal heating to hundreds of millions of square feet of residential and commercial space. Without the massive, uninterrupted volume provided by systems like the Transco pipeline, regional power plants will be forced to shut down their turbines. The Eastern Interconnection, the massive electrical grid linking the eastern half of North America, will face catastrophic load imbalances. The East Coast will experience systemic rolling blackouts. Industrial manufacturing will instantly halt. If this rupture occurs during the winter months, the sudden loss of direct thermal heating will trigger a secondary, immediate humanitarian crisis across the Mid-Atlantic and New England. This is the macro-level threat of the new Madrid seismic zone. The earthquake happens in Missouri, but the power goes out in Manhattan. The kinetic energy destroys the bedrock, but the logistical failure stops the empire. To understand the economic hemorrhage of a mid-continent rupture, you must stop looking at the Mississippi River as a body of water. You must look at it as a colossal industrial conveyor belt. It is the most cost-effective and critical agricultural export corridor on the planet. Every single year, the Mississippi River barge port system moves roughly 500 million tons of shipped goods. When the American Midwest harvests its crops, the sheer volume of that yield requires a logistical capacity that trucks and trains simply cannot handle alone. 60% of all grain exported from the United States is shipped down this single muddy channel. Close to half of all American corn, soybeans, and wheat rely on this exact waterway to reach global markets. The scale of this transport is difficult to conceptualize. A standard 15-barge tow, a common sight pushing through the current, carries the cargo equivalent of 1,050 semi-trucks, or 216 rail cars. Now, imagine what happens when that conveyor belt instantly stops. When the new Madrid seismic zone detonates, it does not just snap the bridges above the water, it fundamentally destroys the navigability of the river itself. The kinetic energy of a 7.7 magnitude event will violently alter the topography of the riverbed. As we saw in the winter of 1812, tectonic uplift and sudden subsidence will create new waterfalls, physical dams, and violent fluvial tsunamis. But in the modern era, the river is also heavily engineered. The upper Mississippi operates using a delicate, cascading system of locks and dams. These are aging, rigid concrete structures holding back immense reservoirs of water. When the deep sediment liquefies, the foundations of these heavy concrete dams will undergo catastrophic, asymmetrical settlement. The locks will shatter. The containment will fail. Furthermore, the river channel will instantly fill with impassable debris. Thousands of tons of sheared steel from collapsed interstate bridges will plunge directly into the shipping lanes. The massive subterranean transcontinental pipelines crossing beneath the river will rupture and float upward, creating jagged, explosive hazards just below the water's surface. The violent kinetic waves will strip the riverbanks, dragging ancient, submerged trees and millions of tons of displaced mud into the main channel. The Mississippi River will instantly transform from the nation's premier logistical superhighway into an unnavigable, toxic debris field. You cannot detour a barge. When the river is blocked, the barges stop. The immediate result is an unprecedented logistical bottleneck. The agricultural yield of the American empire will be physically trapped in the Midwest. The cheapest, most vital artery for American export will instantly shut down, forcing the entire weight of that massive tonnage onto a highway and rail system that will be simultaneously fractured and paralyzed by the exact same earthquake. The modern American economy does not maintain a safety net. It operates almost entirely on a terrifying principle of zero inventory. In logistics, this is known as the just-in-time supply chain. Retailers, hospitals, and manufacturers do not stockpile months of surplus goods in massive, localized warehouses. They rely on a continuous, uninterrupted flow of trucks, trains, and planes to deliver exactly what they need, precisely when they need it. It is a system built for maximum financial efficiency. It is entirely devoid of resilience. When the new Madrid seismic zone detonates, it does not simply disrupt this flow. It physically shatters the most critical logistical hub in the nation. Memphis, Tennessee, is not merely a regional city. It is the geographic center of American freight. It is one of only 4 metropolitan areas in the entire United States served by all 5 Class 1 railroads. This unmatched intermodal connectivity allows domestic freight to reach 45 different states within 48 hours. When the deep alluvial sediment beneath Shelby County turns to pressurized liquid sand, the steel rails of these massive rail yards will violently warp, buckle, and sink into the earth. The rail network will instantly sever. Simultaneously, the trucking industry, which carries roughly 73% of all domestic freight tonnage nationally, will hit an unyielding, impassable geographic wall. The critical intersections of Interstate 40 and Interstate 55, which funnel massive volumes of north, south, and east-west transit across the continent, will be completely compromised by collapsed overpasses, deep fissures, and liquefied approach ramps. With the Mississippi River choked by debris, the rail yards destroyed by soil liquefaction, and the interstates physically broken, the American supply chain will experience a sudden, synchronized cardiac arrest. The countdown to a nationwide crisis begins immediately. Within 24 hours, the massive container ports on the coasts will begin to violently backlog, unable to successfully send imported goods inland. Within 48 hours, manufacturers that rely exclusively on just-in-time delivery for their mechanical components will be forced to shut down assembly lines, triggering widespread, immediate industrial paralysis. But the true existential threat materializes at the 72-hour mark. Within 3 days, the sudden disruption of continuous freight delivery will physically drain the shelves of grocery stores nationwide. Because of the lack of centralized warehousing, perishable items, milk, bread, and fresh produce will simply vanish. Hospitals, which rely on strict daily deliveries of essential medical supplies like syringes, IV fluids, and catheters, will run completely out of critical inventory. Municipal water treatment plants, suddenly unable to receive their weekly rail shipments of purification chemicals, will no longer be able to guarantee the safety of the drinking water. The public assumes that essential goods are local. They are not. They are constantly in motion. When an invisible intraplate fault stops the trucks and snaps the rails, the entire civilization exhausts its supplies in less than a week. We measure standard natural disasters in billions of dollars of localized damage. We measure a new Madrid rupture in direct fractions of the American gross domestic product. When a hurricane destroys a coastal city, the broader national financial system absorbs the blow. Insurance companies disperse the risk globally, the federal government injects concentrated relief funds, the localized economy slowly rebuilds. But a catastrophic, mid-continent intraplate rupture physically breaks the very mechanisms of financial recovery. To understand the scale of the financial hemorrhage, we must look at the data generated by the Mid-America Earthquake Center and the Federal Emergency Management Agency. When researchers modeled the impact of a major event across the 8-state blast radius, the numbers ceased to resemble a natural disaster and began to mirror a sudden, systemic economic depression. The direct, immediate economic losses, the literal cost of shattered buildings, collapsed bridges, and ruptured infrastructure, total nearly $300 billion across the 8 most heavily impacted states. The state-by-state breakdown is a ledger of total structural ruin. In Tennessee alone, total direct economic losses surpass $56 billion. The modeling projects that over 250,000 buildings in the state will suffer moderate to severe structural failure, generating over 60,000 expected casualties and instantly displacing more than 260,000 residents. The destruction moves outward from there. Kentucky faces roughly $45 billion in direct physical losses. Missouri follows with nearly $40 billion in immediate destruction, an estimated 15,000 casualties, and the structural compromise of over 80,000 buildings. Illinois faces $35 billion in damage, while Arkansas and Mississippi incur $19 billion and $9.5 billion in losses, respectively. But the physical destruction of brick and steel is not what terrifies the economists. The true nightmare is the insurance protection gap. If a house burns down, the homeowner rebuilds using their policy. If a massive earthquake levels an entire region of the American Midwest, the vast majority of homeowners are entirely financially abandoned. The Missouri Department of Insurance released a sobering assessment. The estimated damage to uninsured residential properties in that state alone from a magnitude 7.0 to 7.9 earthquake sits at a staggering $100 billion. Because catastrophic earthquakes happen so infrequently in the central United States, the localized insurance market has quietly collapsed under the weight of escalating premiums. Between 2000 and 2014, earthquake insurance premiums in the most vulnerable counties of the New Madrid area skyrocketed by more than 500%, with one county experiencing a nearly 700% increase. Consequently, coverage rates plummeted. In 2000, over 60% of homes in the immediate fault zone were insured against earthquakes. By 2014, that coverage rate had dropped to a dismal 20%. There is no safety net. There is no private capital. There is only ruin. This unprecedented lack of private insurance guarantees that the burden of reconstruction will fall entirely on the public sector. State regulators explicitly acknowledge that an uninsured loss of this magnitude would necessitate a historic, unprecedented infusion of public funds to prevent total societal collapse in the region. But the federal government will be attempting this bailout at the exact moment its own tax revenues are plummeting. Because the New Madrid fault sits directly beneath the logistical heart of the American supply chain, the indirect economic losses will brutally dwarf the physical damage. When the Mississippi River becomes impassable, when the rail yards of Memphis warp into liquid sand, and when the transcontinental energy pipelines snap, businesses across the entire country cannot operate. This triggers massive, cascading business interruptions and catastrophic losses of global market share. Financial models and historical experience confirm that these indirect, secondary economic losses will be at least twice as high as the initial $300 billion of physical damage. We are looking at a total economic impact rapidly approaching $1 trillion. It is uninsurable, it is uncontained, it is economically terminal. This is not a localized recession, it is a sudden violent shockwave capable of visibly shrinking the national gross domestic product in a matter of days. When the shaking finally stops and the immediate rescue operations conclude, the federal government will face an unprecedented reconstruction effort. But the New Madrid seismic zone presents a terrifying logistical paradox. How do you rebuild the logistical hub of the American empire when the tools required to rebuild it cannot physically reach the zone of destruction? Modern infrastructural recovery is not performed with hand tools. It requires massive, specialized, heavy machinery. To reconstruct the shattered suspension bridges across the Mississippi River, engineering teams must deploy ultra-heavy crawler cranes. These are not standard vehicles. A high-capacity crawler crane, such as the Cabelco SL4 500G, weighs over 400 US tons. In extreme cases, ultra-heavy models used for massive industrial lifts can possess a gross weight exceeding 5,000 metric tons. Furthermore, the replacement parts themselves are geographical burdens. A single, prefabricated steel highway bridge girder is a massive structural element designed for extreme load capacity. You are attempting to move hundreds of tons of solid steel across a shattered landscape. Physics dictates a brutal reality for moving this equipment. You cannot fly a 400-ton crane into a disaster zone. You cannot magically drop a steel bridge span from a helicopter. You must transport these assets via reinforced heavy-load rail lines, or you must drive them across rigorously engineered, intact concrete highway overpasses. But a 7.7 magnitude intraplate rupture explicitly destroys these exact pathways. As post-disaster logistical models demonstrate, the fundamental bottleneck in earthquake recovery is the immediate failure of the transportation infrastructure. Post-earthquake field studies consistently prove that damaged evacuation routes, delayed information, and inefficient logistical coordination paralyze the recovery phase. In the Midwest, this bottleneck is exponentially worse. The deep alluvial soils of the Mississippi Basin will have liquefied, swallowing the isolated footings of the region's infrastructure. The railways will be violently warped by the kinetic shear waves. The concrete highway overpasses will have collapsed into impassable rubble. The Mississippi River, choked with tectonic debris and shattered locks, will be entirely useless for heavy barge transport. This is the recovery paradox. The American Midwest will require thousands of heavy machines to clear the rubble and rebuild the arteries of commerce. But those machines cannot be brought into the impact zone because the arteries of commerce are completely shattered. Engineers cannot simply pave a temporary dirt road over a recently liquefied floodplain to move a 400-ton machine. The load capacity, the sheer weight the ground can support without physically caving in, will be severely compromised. The ground will yield. The equipment will sink. Because of this, reconstruction cannot happen simultaneously across the 8-state blast radius. It must happen sequentially, painfully inching inward from the surviving outer perimeter. Construction crews will have to spend years just rebuilding the approach roads required to bring in the cranes required to rebuild the bridges. The disaster zone effectively becomes a geographic fortress, actively repelling the heavy equipment required to save it. This is why the recovery will not be measured in months. It will be an agonizing, decades-long endeavor. There is a dangerous, comforting myth that occasionally circulates about the new Madrid seismic zone. It is born from a misinterpretation of modern satellite data. In recent decades, geologists placed highly sensitive GPS instruments across the Mississippi River Valley to measure the physical deformation of the Earth's crust. The data returned a seemingly reassuring result. The surface of the ground is barely moving. Some theorists pointed to this lack of surface strain and argued that the fault was fundamentally dead. They suggested that the minor earthquakes we feel today are simply a 200-year-long aftershock sequence from the winter of 1811, and that the geological engine had finally shut down. But the United States Geological Survey and the broader scientific community have explicitly rebuked this conclusion. We must return to the terrifying mechanics of an intraplate fault. The lack of visible surface movement does not mean the tectonic engine has stalled. It means the system is perfectly rigidly locked. The stress is not venting. It is actively accumulating. Because the ancient bedrock of the North American craton is so dense and cold, it absorbs and stores elastic strain deep underground without warping the surface mud. The pressure cooker is not turned off. The lid is simply bolted shut. This is not a hypothetical threat. It is a cyclical certainty. By digging into the alluvial soil and carbon dating the massive sand blows left behind by prehistoric soil liquefaction, geologists have unearthed the fault's terrifying operational schedule. The new Madrid seismic zone did not wake up for the first time in 1811. The subterranean record proves that catastrophic multi-quake sequences of a similar magnitude detonated around 1450 AD. And before that, around 900 AD, the geological math is unforgiving. The fault detonates on average roughly every 500 years. The United States Geological Survey does not deal in panic. They deal in probabilities. Their current modeling projects a 7 to 10% probability that a catastrophic earthquake of magnitude 7.5 to 8.0 will strike the new Madrid zone within the next 50 years. For a highly destructive magnitude 6.0 to 7.0 event, that probability skyrockets to between 28 and 46% within the same timeframe. These are not trivial odds. They are a ticking clock. The bedrock beneath the Midwest is still ancient. The tectonic forces of the North American plate are still pushing. The 3,000 feet of alluvial sediment beneath Memphis and St. Louis are still saturated with water. The heavy, unreinforced masonry of the heartland is still completely unequipped to survive a massive shearwave event. The subterranean monster did not die in the winter of 1812. It simply went back to sleep. And every single day, the invisible elastic strain building deep inside the real foot rift brings it one day closer to waking up.